So this is Unit 1, Lesson 4, Linear and Absolute Value Inequalities as opposed to equations. The objective: students will solve linear and absolute value inequalities as well as graph the solutions on a number line. Now in class we didn't do it to these notes. I wanted to put them online so that you would have them at home. But on class we did the Understanding Math tutorial on this. Now we have an inequality whenever instead of an equal sign you have greater than, less than, greater than or equal to, or less than or equal to. In this case I have x is greater than -3. That's going to mean that all the solutions are all the possible numbers that make that statement true. So I could have -2, I could have +2, I could have 4, I could have 7, I could have 9. Anything that's bigger than -3 makes that a true statement, and so then are all acceptable values for x. That then means that there are an infinite number of solutions, so I can't write them all, so I have to show them on a graph. In this case, I'll put a circle around -3 to indicate that that's where I start. Now in this case the circle is open because -3 is not a potential solution. If I put -3 is greater than -3, that would be wrong. So I put a circle to indicate that -3 is not a part of the solution. And I shade the graph to the side that represents the numbers that are greater than -3, and greater than always goes to the right. Another example, I could have x is less than or equal to 4, so I put the dot on the 4, and this time, since 4 would be a proper solution, that is, if I plugged in 4 for x, 4 is less than or equal to 4. It's the or equal to part that makes that true. So I put a solid dot to indicate that the 4 is part of the solution, and to shade less than, I shade to the left. And so my solution on the graph would look like that. In this case, we have what's called a compound inequality. In this one, we have x is greater than or equal to 2, or x is less than -1. Now, the set of solutions to this is going to be all the solutions that make one of those two things true. So, if I had 4, where I would 4 is greater than or equal to 2, that is true. So that would be an acceptable solution. If I had -4, -4 is less than or equal to -1. So the second one would be true, which means we're in an acceptable solution. But if I had something like 1, then that would not be true because x1 is not greater than 2 and 1 is not less than -1. So I'm going to have two different sets. First, a set of all numbers that are greater than or equal to 2. So I put a solid dot on 2 because it's or equal to. I shade to the right because it's greater than. And on the other side, I put an open circle because it's less than, not or equal to, just less than. And I shade to the left because it's less than. If you want to get full credit for this problem, you would have to have both parts of this graph. Another type of compound inequality, that's one inequality that has two different parts, is an AND statement. So an AND statement has two statements, and in order to have a correct solution, both parts of the statement have to be true. So in this case I have x is greater than or equal to -3 and x is less than 0. So in this solution something like 4 would work for the first statement because 4 is greater than or equal to -3, but it would not work for the second statement. 4 is not less than 0. So 4 would not be a part of the solution set. And something like -4 would also not be part of the solution set because it doesn't meet both equations. It doesn't meet both inequalities. -4 is not greater than or equal to -3, so that would not be a part of the solution set. So in order to graph an AND inequality, I first mark the greater than or equal to -3, and it's or equal to, so it's a closed circle on -3. I put an open circle on 1 because there's no or equal to, and the only acceptable solutions are the numbers that come in between those two dots. So that would be the graph of the solution set. I could rewrite this a little bit differently though. Since if x is greater than or equal to -3, another way to write that is that -3 is less than or equal to x, which is in turn less than 0. So I can combine those x's. Sometimes you'll see the AND inequalities written like this. -3 is less than or equal to x, which is less than 0. Now, to solve linear inequalities. An inequality is anything that uses less than, greater than, less than or equal to, greater than or equal to, instead of an equal sign. So to solve them, you do the same thing you would do for equations, and there's only one thing you have to remember that's different. When you multiply or divide by a negative number, you have to reverse the sign. You have to flip the sign. Less than becomes greater than, less than or equal to becomes greater than or equal to, and vice versa for both of those. So here's an example of a linear inequality. Now I solve it the same way I solve an equation, only I have a less than or equal to sign instead of an equal sign. So I would still first subtract 3 from both sides. That's going to get me negative 2x is less than or equal to 8. Now I divide by negative 2, and that's going to give me x and 4. But remember, when I divide or multiply by a negative number, the sign has to become reversed. So this is x is greater than or equal to negative 4. To show that on a graph, it looks like that. A solid dot at negative 4, the answer's going off to the right. It's very important that you remember to flip the signs when you multiply or divide by a negative number. Now, absolute value inequalities become compound inequalities. We already said that the equation is two different things, so is the inequality. This means either x minus 4 is less than 3, or negative 1 times x minus 4 is less than 3. And we solve them both. So if x minus 4 is less than 3, then that means x is less than 7. You just add 4 to both sides. And if negative 1 times x minus 4 is less than 3, first we have to distribute the negative 1. That gives us negative x plus 4 is less than 3. Subtract 4 from both sides. That's negative x is less than negative 1. So we have to divide by negative 1 so we can get positive x. When we divide by negative 1, we have to flip the sign. So that gives us x is greater than 1. So in this case, that's what the solution looks like. They're both greater. It's less than 7, so you start shading to the left. It's greater than 1, so you start shading to the right, and you'll see that this is an AND inequality with a shading that goes in between the two. Just to show you a little more complicated of an example, we have the absolute value of 3x plus 5 is greater than or equal to 10, and we know absolute value always means two things. It could mean that 3x plus 5 is greater than or equal to 10, or it could mean that negative 1 times 3x times plus 5 is greater than or equal to 10. Solving the first one's not too difficult. You subtract 5 from both sides. You get 3x greater than or equal to 5. You divide by 3. Gives you x is greater than or equal to 5/3, which is 1 2/3. Negative 1 times 3x plus 5. We distribute the negative 1. We get negative 3x minus 5 is greater than or equal to 10. Add 5. I get negative 3x greater than or equal to 15. Divide by negative 3. And remember that when you divide by a negative number, you flip the sign. So we have x is greater than, less than or equal to negative 5. Putting that on a graph, remember 5 over 3 is 1 2/3, and it's greater than that, so it goes off to the right. X is less than or equal to negative 5, so you put it in negative 5, and you go to the left for less than. So whenever absolute values are greater than, the graphs go in opposite directions, away from each other, and whenever it's less than, they go in the same direction. It's an AND inequality. So there's the homework for today. Don't forget to include the graphs. The graphs are part of the answers, and so they are required. Good luck, and I'll see you next class.